Okay, folks, here we are. We're backtracked to 8C, integration using a CAS calculator. Look, word of warning, it's a little bit of a quirky um, exercise, this one. It's kind of on the fringes of the course. It poses some interesting mathematics, but certainly some quirky mathematics. Do your best to follow along. It's not super important, and come and see me if you've got any questions about it. Okay, have a look at this one. Use a CAS calculator to evaluate that. All right, now, of course, um, you guys know where the integration feature is in your CAS calculator. No need for me to go over it. It's well and truly discovered. Not much to explain here. Remember, if it says evaluate to 3 decimal places, it's always code to pick up your CAS calculator and have a go. How about using your CAS in this particular instance? So you've got to find, here's your graph. It's e to the sine x minus 2. Interesting looking graph. Obviously, the power oscillates between values of -1 and +1, and the graph is shifted down by 2. Okay, so you have to find the area bounded by the curve and the x-axis between pi on 2 and 3 pi on 2. So this is one approach, is to firstly determine from what is the value of a, integrate from pi on 2 up to that a, and then plus the negative of the integral from a to 3 pi on 2. Have a look what I've got. I've actually not appropriately set my interval on which to look for a solution. Let me just grab that pen. You can see there, I should have really had a lower bound of pi on 2 to 3 pi on 2. So it's led to a potential, well, a solution that's not relevant. It's obviously a value for x that lies outside of my interest. So it's a value lower than pi on 2, which is about 3.14 divided by 2. It's clearly not in the domain I'm interested in. So I choose the correct. Let me just get rid of this pen. I choose the correct one. Okay, there's just a comment about the restriction. And of course, anytime you're solving an expression or an equation set to 0 involving a trig function, you must always impose that restriction. Otherwise, you'll get a quirky answer. My imposed restriction wasn't strict enough. Nevertheless, I should be able to work out what is the value of a in this particular case. There's my value greater than pi on 2, greater than 1.5, less than 3 pi on 2. Okay, then I can set up my integrals. Okay, so, and I have to, actually it doesn't say, interestingly, it doesn't say to 3 decimal places, but that's what the answer here is providing. Now, in fact, there is no exact answer. Even if you set your calculator to the right setting, there is no exact answer. It can only approximate. It's a numerical approximation for a solution. Now, hopefully some of you in the crowd will be looking at that and thinking, why bother even find a? What about that old technique of setting the modulus of the function and just simply taking the integrating over the interval pi on 2 to 3 pi on 2? And of course, surely that would give you exactly the same answer, and indeed it does. So you can see before you, without even needing to worry about where it's crossing the x-axis over the required interval of x, the use of the mod gets you there. So if you've got use of a calculator, why on earth wouldn't you perform that little trick? Okay, so a big part of 8C is these net signed area functions. So have a look at this. It's probably something you've never seen before. You've got some function defined as the antiderivative of 1 to x. So x is the unknown of the integrand. Now the integrand, let me just grab a pen. The integrand is this. It's with respect, it's using a dummy variable. It's using some variable, not x, in order to express it. It wouldn't make sense to work with x because x becomes the the upper bound, the upper terminal in this integral function. But have a think about what this is creating. So let's just click on this. Okay, that's obviously 1 on x, and what we're interested in is a function that as x is growing, in other words, as x is growing in the positive direction from 1, so obviously that's the point 1, comma 1. Okay, as x is growing greater than 1, it's sweeping through a bigger and bigger area. So x is going to sweep through a bigger and bigger area as x is growing. So this is an increasing function for values of x bigger than 1. The larger x is, the greater the value of the function is, but you see it's going to grow at a smaller and smaller rate. So as x moves in the positive direction, we're actually only increasing the value of the function by smaller and smaller amounts. Okay, now let's just have a think about this. So there it is. So I've got, oh, actually, hang on. So we've got, if I was to replace x by, so in here, I've got an up, what I'm doing is determining the area from x equals 1 to x equals 4.02. It's about 1.1, it's about 1.419. Well, what is that value, and why is it that it's going to be approximately equal to the natural log of that x value of 4.029? Why do you think that is? What's going on here? Okay, so there it is. If we were to think of the function f of x defined in this way, on a restriction that x is greater than 1, what we've got is part of the log graph. So let me just grab a pen here. Let's make sense of this. So if I was to anti-derive 1 on t over an interval 1 to x, where x is the upper bound, so here's our definition for x, 1 on t dt. Remember, you have to use a variable other than x in this setup. What we have is the natural log of t. Now I don't need to put a mod around that because x is greater than 1. Okay, from x to 1, leading to the natural log of x minus the natural log of 1. Natural log of 1 is 0, leading to the natural log function. Okay, so that's the curve you see before you. It's a part of the natural log function. All right, this, in fact, what we could do, in fact, and just to appreciate where we're at, therefore, here is our 1 on x, 1 on t function. We're starting it at 1, 1. There's x. There's a value of 1, x equals 1, and as x is growing larger in this direction, this area becomes equivalent to, there's our upper bound x, becomes natural log of x. So it's describing an area function, a net signed area function. All right, what happens if we were to allow values of x not just greater than 1, but greater than 0? What would the graph look like? Let's have a think about it. So for x is proper fractions, in other words, positive proper fractions. So let's have a think. So suppose x we allowed to be equal to a quarter. Okay, so our f of x will be equal to 1/4 to 1, 1 on t dt. Now, because a quarter is less than 1, we're expecting a negative value. We've got natural log of t, 1/4 to 1, and we sub in 1/4 minus natural log of 1, which as we know is 0, and that's equivalent to minus natural log of 4, a negative value. And you can see as x approaches 0 from the positive side, as x gets smaller and smaller and smaller, a quarter, a tenth, 100th, etc., etc., f of x will get larger in the negative direction, will approach negative infinity, okay? In other words, the graph, our net signed area graph, will start to resemble the full natural log graph. Okay, is that making sense? So if I'm integrating from 1 to x, okay, from x to 1, I get an increasingly large area, but from 1 to x, if I reverse the terminals, I get a negative area. So it's all matching up nicely as well. All right, talk about quirky little questions so that you might enjoy this one. Use a CAS calculator to find an approximate value of the definite integral 0 to pi on 3 of cos x squared dx. And to plot the graph of f of x equals 0 to x using dummy variable. Remember, if I've got a net signed area function, some initial value to the open-ended upper bound, it has to be a variable other than x. So t is the go-to. So we're talking about x taking on any value from minus pi and 4 to pi. Now, of course, this value can be obtained directly from your CAS, no big deal. But let's have a play with this net signed area function and see what we come up with. Okay, so the value of this definite integral becomes the value of the area function under the cos x squared graph from 0 to pi on 3. Okay, so that's what f of pi on 3 represents, the area under the cos x squared graph from 0 to pi on 3. All right, so if we're asked to actually get the calculator to redefine it, it can't. And the reason being is there is no natural description. So the area function can't be simplified to something nice and neat. So it keeps that, definite integral expression. Now, when we do graph it, we set that particular rule into our graphing screen. We get a function like that, an interesting looking function. And if we type in x equals pi on 3, which as you can see there is approximately 1.047, so that would be pi on 3. We sub it into, we can use our gsolve and ycalc to determine the approximate y value, and you've got 0.9281 it looks like, or 6181 I think. Okay, and that would be equivalent to just that value is what you should get when you just whack that into your CAS directly. So it's working out, it's a net signed area graph, and it's telling you the net signed area when x hits pi on 3 under the curve y equals x squared. Let's analyze this a little bit more to see if we can make more sense of this. Okay, there is the net signed area curve from 0 to various values. We typed in a value just above 1, which resulted in pi on 3, and we had a y value of 0.9281, something like that. What's going on here? Why is it that our function is dropping? So you can see here it's continuing to pick up speed. It hits some particular value of x, and then it starts to decrease. What do you think is representing that decrease? Hits another x value over here and starts to increase to a point, and then does a decrease yet again. How is that related to our cos x squared graph, or a cos t squared graph, and the understanding that we're talking about a net signed area function? What would account for that drop in our net signed area? So if you were thinking something along the lines of, well, it must be where the graph is dipping below the x-axis, then you'd be dead right. So here's what I've done is just done a ycalc situation. So clearly when x, I've just whacked in a value, x equals 2.4786, and I've got a y value of 0.58. But what's going on here? Let's have a think about it. Okay, so I've now got the CAS to just sketch y equals cos x squared from minus pi on 4 to positive pi. And you can see, therefore, what's going on. See if you can find the connections between the two graphs. So at this point here would equate to this point over here on our net signed area graph. So the graph is making positive gains as x is getting larger and larger from 0. We're sweeping out a larger area under the cos x squared curve. It hits that particular value of x, and then it starts to contribute negative area, hence the dip. Okay, hence the dip. It drops at the greatest rate at some point, and then a smaller and smaller amount of negative area is contributed until it hits this point over here. Let's just call it A and B, related to A over here and B over there. Okay, now we return to a positive signed area until we hit that 2.4786, 2.4876, and in fact the area that I've swept out, the net signed area, so that's here, let's call that point C, is I've got the calculator on the left. Let me just get rid of some of this stuff. So you can see the calculator has got the net signed area. It's swept through from x equals 0 to 2.4786, 2.4786, and it's got this area indicated over here, 0.57, and that's simply the value of the function at x equals c. So there it is over here, the value of the net signed area function. But you can see the key points. So again, A occurs here. It then starts to, the net signed area function starts to dip to account for the inclusion of a negative area. The net signed area drops. We then pick up again after B until we hit that point C. And if we were to keep going, it would continue to gain some area, albeit less rapidly. It hits that point D, where it then starts to drop off again, and so on and so forth. So there's the connection between the two. All right, I've got a further question for you interested punters out there. You can see for negative values of x, over here, remember from x is 0 up to minus pi on 4, you can see that the cos squared graph is above the x-axis. Therefore, why does it drop away in the negative direction over here? What's causing our net signed area function to be negative for values of x between minus pi on 4 and 4 when you can see clearly, hang on, let me just get rid of this, when clearly the function, the cos squared function is positive, is in the top half of the graph. I wonder if you can see what's going on there. Let me just make it clear. Here's our original function. So just to make it clear, let's get rid of that. So why is our net signed area function negative for negative values of x between minus pi and 4 when the cos squared function is clearly not negative, is above the x-axis over there? Well, you can see, hopefully, those of you on the ball, when x is negative, what we're doing is integrating from 0 to a value lower than it. And so what the integral is doing is making that, therefore, a negative value. So even though this is positive, because we're integrating, say, from 0 to, what's the value, less than minus pi on 8, say, okay, cos x squared dx, that'll, of course, be the same thing as negative 0 to minus pi on 8 cos x squared dx, which we know is a positive value. So this here is positive because the graph is positive, is above the x-axis, but because the terminals have been, we're going from a lower bound to an upper bound where the upper bound is lesser, it means it's interpreting as a negative value. Now, this is all analysis. It's unlikely you'd ever be tested on this truly, but it's interesting to explore these functions, these net signed area functions, but certainly do not get too concerned by them. They're right on the fringe of the course. Okay, so let's finish off with this particular example. The rule for the function is defined as an area function. Okay, we're defining it for any value of x, both positive and negative. So we'll think about the ramifications for that in a minute, which are quite interesting. All right, so let's go through the process of trying to get a neater definition of f of x. We should be able to do that because we can certainly antiderive sine t. We know the antiderivative is negative cos t. I'll just section out the negative, upper bound x, lower bound 0. This is what f of x is equal to. Okay, which is equal to minus brackets cos x minus 1, which is in fact 1 minus cos x. Now cos x, which is a function that can take on any value from minus 1 to positive 1, clearly this is a function whose range is anything from 0 to 2. Now you might ask yourself, hang on, that's a bit curious, but let's have an explore and see why this makes sense. So as x is growing larger and larger and larger, clearly this point here is pi, as x is growing from 0 to pi, our area goes from, okay, so let's say f of pi will be 1 minus 1, which is 2, so it's reaching its maximum net signed area. And as x is growing larger, continues to grow larger, so there's obviously 3 pi on 2 minus 1, we're starting to bring in a negative area. So f of 3 pi on 2 will be equal to 1 minus cos 3 pi on 2, which as we know is equal to 0. We've got our area of 1. Okay, so here's an area of negative 1, here's an area of positive 1, and so on and so forth. So it'll continue to grow in that direction, making perfect sense. A net signed area function. Curious situation when x is less than 0. Okay, it's a curious situation. Does this rule still hold for the net signed area? Well, it does and it doesn't. There's a bit of a limitation on understanding x as our upper bound. So let's think about it in the negative direction. So as we go over here at minus pi, surely would have an area of negative 2 is what our function should be saying. So f of minus pi, according to our rule, is 1 minus cos of minus pi, which is 1 minus 1, which is 2. Why is it positive 2 when clearly that sine area is below the curve? And it's exactly for the reason we've discussed before. If our upper bound is less than our lower bound, it'll be the negative opposite. So it's kind of effective as a net signed area function up to for positive values of x. For negative values of x, it's the opposite. So what we're doing is, of course, integrating from minus pi to 0 in this particular case, sine t, and getting the negative opposite of the integral minus pi to 0, sine t dt, which turns out to be negative of negative 2, which is positive 2. All right, so you get the idea, don't you? Okay, I think that's all good. All right, we'll leave it at that. I think we're good from there. Okay, good. See you for now, folks. I was going to do the length along a curve, but we'll save that for the next time I see you in class. Please make sure you listen to these vodcasts and are up to date next time I see you, which will be next Friday. That'll be bye for now.